As we start this new unit on derivatives, I just wanted to quickly remind you that in the previous chapter, we were using the first principles for derivatives. This chapter is going to be giving us new rules that we can use so that we can use our time more quickly and efficiently. So there are various ways a derivative can look, but they all mean the same thing. So if you've been reading ahead, or if the last chapter made you curious and you did a little bit of research online, you may have seen some of these. So prime notation is what you have been used to, I guess. So when we're writing something or a derivative using prime notation, you'll see it as y prime, or even f prime of x. So when you write either of those things, what you're telling me is that the answer that you're getting, or what you're writing, is the derivative. The next form that is on this list is Leibniz notation. Now, you may have seen this before. It is dy by dx. So if you were going to write this, dy by dx. You may also see this or hear this being referred to as the derivative of y with respect to x. Our third and final notation is operator notation. This is probably the least used notation, but if y is equal to x squared, then d of x squared with respect to x, or the derivative with respect to x, is how you would say that one. We're going to jump right into derivative rules. So the first rule that we're going to be discussing is the constant rule. So if we had a line y equals a number, or a horizontal line, the derivative of that will be 0. Our constant rule says that if f of x is a constant function, so f of x equals a number, c, then the derivative of f of x, or f prime of x, is equal to 0. So if we picture a horizontal line, so y equals any number, the slope of that line at any point throughout that whole graph will always be 0. Now when we're finding the derivative, that is exactly what we're finding. We're finding the slope of the tangent. I'm just going to go through two examples really quick. So if we have a function f of x is equal to pi, since we know pi is just a number, we can easily just say that f prime of x, or the derivative, is equal to 0. Now if I were to graph this, we know that this would be a horizontal line at pi, and the slope of the tangent at any point on this graph is 0. My second example is f of x is equal to root 2. Now again, there's no letter in here, there's no x variable, and so we know that this is a constant and the slope will always be 0, so my derivative is equal to 0. Now again, this is just a horizontal line at root 2, so again, we have the slope of the tangent being 0. Our second rule is called the constant multiple rule. So if we have a function g of x that equals a constant, or c, times another function f of x, then the derivative of g of x, or g prime of x, is equal to that constant c times the derivative of f of x, or f prime of x. So we're going to go through a couple of examples. So in example 1, we have that g of x is equal to 3x squared, and we have that f of x is equal to x squared. So what I can see right away is that g of x is really just equal to 3 times f of x. In terms of derivatives, what we can then say is that g prime of x, or the derivative of g of x, is equal to 3 times the derivative of f of x, or f prime of x. Our third rule is the sum and difference rules. So if f of x and g of x are differentiable, so if you can take the derivative of both of them, then so is f of x plus g of x and f of x minus g of x. And this is what their derivatives would look like. So as I'm sure you can see, this rule is pretty intuitive. So when you look at this, it's saying I'm combining two functions here, so f of x plus g of x, and if I wanted to take the derivative of that, it would be the derivative of f of x plus the derivative of g of x. Same thing with the combination f of x minus g of x. So the derivative of that function combined would be the derivative of f of x minus the derivative of g of x. In the next slide, I am going to be doing a proof of this sum, so f of x plus g of x prime. And to do this, I am going to be using my algebra and my first principles. As I'm starting this proof, I did just want to remind you that the whole goal of this proof is to get the left-hand side to equal the right-hand side. So if I'm attempting to prove this, the first thing that I'm going to do is say let capital F of x equal f of x plus g of x. Since I've done that, I can then start using my first principles and say that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all divided by h. So as you can see in this next line that I wrote here, I've just plugged in the information that I've given. I just wanted to remind you that I did use square brackets here so that I could remember that this whole thing is being subtracted. In the next line, since my goal is to get what I have here on the right-hand side, I am going to be grouping all of my f's together and all of my g's together. Now, because we've already discussed limit rules, we know that we can take this limit now and break it up into two separate limits. So one limit that's only involving my f's and one limit that's only involving my g's. So what I have here is the limit as h approaches 0 of f of x plus h minus f of x divided by h, plus the limit as h approaches 0 of g of x plus h minus g of x divided by h. Now what you're probably noticing is that each of these do represent something that you've already seen before. This is just the formula from our first principles. So really this is just f prime of x plus g prime of x. And what we've done is proved exactly what we wanted to prove. So now we know that the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. Notice how I worked through this whole proof using f of x and g of x. I didn't just pick one specific function for f of x and one for g of x and prove that it worked for that function. By doing this, I'm proving that it works for all functions. Our fourth rule is the power rule. This is the rule that most of you discovered in the last unit. So if f of x equals x to the n, where n is any real number, then f prime of x is equal to n times x to the n minus 1. So of course we're going to go through a couple of examples. So example 1, f of x is equal to 8x cubed. Now we know from finding patterns and even from this power rule above, we need to be taking the coefficient, our 8, and multiplying it by our power of 3. And so we're going to be getting 24 x to the power of 2. And this is because we know that our exponent always needs to decrease by 1. And again, in our rule, it does say n minus 1. So we have f prime of x is equal to 24x squared. Now I don't know about you, but I definitely know that I would rather be doing this than using my first principles every single time and taking up to a half a page or a page to calculate one answer. Our next example is a quartic function. So g of x is equal to 24x to the 4 minus 15x squared minus 2. So what we have here is g prime of x is equal to 4 times 24, so 96, x to the power of 1 less, so 3, minus 2 times 15, so 30, x to the power of 1, because 1 less than 2, and then this constant term at the end goes away. We did discuss this in a previous rule, the constant rule, and so our g prime of x is done. So example 3 is a quadratic written in factored form. Now, if we're going to be using the power rule, we do need to expand this out and put it in standard form. We will be learning a rule later on how to do this the way it is, but for now we are going to have to go ahead and expand that. So y is equal to 2x squared minus x plus 6x, so a plus 5x minus 3. Now that it's in standard form, or it's been expanded, I can do my derivative. So y prime is equal to 2 times 2, so 4x plus 5. Since this is a power of 1, I am essentially doing 1 times 5. And then there is no x because the new exponent would be 0. This constant term goes away, and so my derivative is done. Our fourth example is h of x is equal to 1 over x. So technically, right now, we cannot be using the power rule for this. We do need to rewrite this. So we are going to have to go back into our brains and remember that we could simply rewrite this as x to the power of negative 1. Now that I have this rewritten, I can go ahead and do my derivative. So h prime of x is equal to negative 1 times x to the, my new exponent needs to be negative 1 subtract 1, so negative 2. We know that this is not really proper form, that we should be rewriting this. So h prime of x is equal to negative 1 over x squared. Again, we will be learning how to do a derivative like this right from this form in the next couple of lessons, but for now we can just go ahead and use the power rule like this. For our fifth and final example, we are going to derive the radical function, so y is equal to the square root of x. Now, as I'm sure you're already thinking, we cannot use it in this form, so y is going to have to be equal to x to the 1/2. Now, just as a little side note here, we do know that if we are trying to rewrite something like this, then we have y is equal to the nth root of x to the a. I'm actually going to change this. The nth root of a to the x. We can rewrite that as y is equal to a to the x over n. Now, when we do a square root, it's just assumed that the little n here in the nook is a 2. So now that we've talked about this, I can go ahead and I can derive this. So y prime is equal to, I'm going to bring my exponent down, so 1/2 x to the, now we have a 1/2 as my original exponent, subtract 1, and I'm going to get a negative 1/2. Now, I know that I can rewrite this. I don't like to see a negative exponent like that. So I can rewrite this as 1 over 2x to the 1/2, which is 1 over 2 root x. Now, I am okay with this answer. A lot of professors in your future may not be. So you do know that you could rationalize this. So if I was going to go ahead and rationalize this, I'm going to be multiplying by a root x over a root x, or in other words, a 1 technically. And I'm going to be getting y prime is equal to root x over 2